Okay, now we're going to work our way through this. We're going to do this exactly how we did with series circuits. So, first thing, make sure you're listening. First thing. Second thing, I would highly encourage you to write this stuff down because you will see it again over and over and over and over again. I'm also going to record this and post it so that you can watch it as many times as you need to. So we're going to work our way through this circuit right here. Then, tomorrow, you're going to have to answer a couple of questions in a discussion about parallel circuits. Whenever we all come back, you're going to have a little practice sheet that you're going to do on parallel circuits. Then we're going to start building and constructing parallel circuits. And the big overall project is going to be you completing your own game board, which is a combination of both series and parallel circuits. So it's very important that you understand this stuff. All right, so there's the rules. And I'll roll over here. We'll start working our way through the circuit. As long as you follow the rules, this is not overly complex. And if you follow the rules, you'll be able to catch any mistakes that you make along the way. Because when you're doing the math, it's very easy to make a mistake if you don't pay attention to the rules. If you try to mix series and parallel circuits, you're going to have all kinds of bad results. All right? So, we got two different resistors. Very, very similar to the circuits that we built last week. Those bulbs that we used, with the exception of this one over here, because those are out of a turn signal circuit and a Crown Vic. But these smaller bulbs, we had a slightly higher voltage drop on one than the other, which means that one has a slightly higher resistance value. Very similar to this. 1 ohm difference is not a huge difference, but it is enough to see a difference on the meter. So, we start out with 12 volts, just like we always do. Or if we're doing it actually with that battery, you saw that it was maybe 11.96 or 11.97. But on paper, we're always going to use the number 12. It's a nice even number. So, in a series circuit, these bulbs would have to share that voltage, but that is not the case. Okay? So, what does this little symbol represent? It's a fuse. Is a fuse a resistor? Should we be using any voltage here? Yes or no? Okay? No. We learned that when we did our voltage drop tests. The fuse and the switch should not be using any major amount of voltage. So if we start with 12 volts here, how many volts should we have here? Speak loudly. It's not yes or no. How many volts should we have available right here? If we start out with this number, how much should it change from here to here? It should stay the same, yes. So the number should be yes. Okay? So we're following along here. This is our path of current flow. So if we measured a voltage drop here, we should still have 12 volts. What about across the switch? How many volts should we use here? Should be no volts, which means our voltage would still be how many? 12. Very good. All right. Now, here's where a lot of students get confused. They think because we have two circuits that this is going to get split up 6 and 6. That's not the case. Okay? We have 12 volts available right here. All right? Now, from here to here, we don't have any light bulbs. We don't have any resistors. So we are not going to be losing or using any volts across this section of the circuit, which means that we're going to have the same 12 volts available right here. All right, so in a series circuit, voltage gets divided up or split up in the circuit. In a parallel circuit, it just gets shared. It's not necessarily used or divided up based on the number of branches in the circuit. Each branch should have the same amount of voltage applied, 12 volts. The only exception would be if you had something in the circuit where you purposely wanted to change that. So an example there would be, again, your dash lights. A lot of times they have a rheostat, a little knob that you can turn, where you dim or brighten the lights. So in that scenario, your switch would be able to change the resistance value for all of these bulbs, which is going to raise or lower the voltage. But that's kind of a special circumstance. That's about the only thing on a car that has that option. So, since we have 12 volts available, now we can start working our way down through this. Very first thing that we're going to do is we're going to calculate total resistance. Now, again, make sure that we're following the rules. Very first thing that it says in big bold capital letters is do not add the resistors. In a series circuit, we would just take these two numbers and we would add them together and have 7. But that is not what we're going to do here. We are going to use one of two different options. I'll show you one today, and then I'll show you another one when we come back because I don't want to confuse you by showing you both at the same time. So if you have a circuit with 2 branches, like this, which is very common, you can use what's referred to as product over sum. Okay, so it would look like this. RT, that stands for total resistance, equals product over sum. Now, when you're talking about math, if you are finding the product of something, what mathematical function would that be? The product of 2 numbers is when you take one number and you multiply it with another number. Okay, so this is going to be multiplication. What is the sum? That's when you're adding 2 numbers. Okay, so I'm going to write this down step by step by step by step. So product over sum looks like this. RT equals the product of these 2 numbers divided by the sum of these 2 numbers. So R1 and R2. R1 times R2 over top of R1 plus R2. So that's the actual formula. Now, all you have to do is take your numbers for whatever those values are and put them in those places. So RT equals 3 times 4 over top of 3 plus 4. All right, so now let's do the math. What is 3 times 4? 12. What is 3 plus 4? 7. All right, so now what is 12 divided by 7? It's going to be some decimal. What is it? 1.7. Okay, now if you have a number that's like 1.7546548, just take it out 2 decimal places and probably round it up to the next one. So if this is 1.77777 repeating, we'll just keep it 1.7. But let's just say it was 1.725, then we would just call it 1.73. But 1.7. And also remember, when you're doing this, this is 1.7 ohms. Doing the math is important, but understanding what number that you're representing or what the value is, that's equally as important. So this is 1.7 ohms. Now, we can check our work real quick. I wrote this up here just a second ago. In a parallel circuit, total resistance is always going to be less than the lowest resistor value in the circuit. So, is the number 1.7 less than the number 3? Yes. Let's say you did your math and you got the number 3.7. There's no way that that number can be right. You had to have made an error somewhere because based on the rules, whatever number we get here has to be lower than the number 3. All right? So 1.7 ohms is what we have. Now, we're going to use that to find the rest of this stuff. So there's 2 different ways we can calculate the rest of the circuit. If we want to figure out what amperage is, using Ohm's law, E represents volts, I represents amps, R represents ohms. Anytime you have two of the three values, you can always find the third. So we have our voltage. Voltage doesn't change in this scenario. We have our resistance right here. So what we want to do is we want to take voltage divided by resistance. And that's going to tell us how many amps we have here. So what is 12 divided by 3? 12 divided by 3. Use a calculator. Okay? 4. And we're talking about amps, so it's 4A. We'll do the same thing over here. What's 12 divided by 4? 3 what? 3 amps. Okay? Now, following the rules, total circuit amperage, which is up here, anytime we're measuring this main line, we're talking about the entire circuit. These are individual branches. So total circuit amperage is the sum of all the branch values. So we have 2 branches. If we want to find A1, all we have to do is add these 2 numbers together. So what is 4 plus 3? 4 plus 3. Speak loudly. 7 what? Amps. All right, now, we want to double check this. Anytime we're trying to find one value, if we have 2 of the other values, we can always find the third. So, we know that our voltage in this circuit pretty much never changes. It's 12. We have our total resistance value of 1.7. So, take 12 divided by 1.7. Seven even? Okay, so 7.05. Anytime that you add branches to the circuit, you're going to have to deal with some decimals. So we just proved that all this is correct. 12 divided by 1.7 gives us 7.05. So that would round down to 7. It might wind up being 6.99. You would round that up to 7. So keep that in mind when you're dealing with parallel circuits. You're probably going to have to do a little bit of rounding up or down. But this is within, a tenth of an amp, which means that the math is going to be correct. So, 2-branch parallel circuits, this is how you can find total resistance. Now, if you have a 3-branch parallel circuit, meaning that we have an additional branch, there's another way that you can find it, and I'll show you that on a different day because I don't want to confuse you. But just like that step over there, I highly encourage you to write this down. You're going to see it again, probably more than once. You're probably going to be asked to answer a question in regards to that on a discussion tomorrow. Now, the last thing is voltage drop. Voltage drop in a parallel circuit is actually a little bit easier than voltage drop in a series circuit. So when you're looking at this, you can think about this branch as one series circuit. And you can think about this one as another series circuit. It has its own individualized path to ground. We have 12 volts available right here. We only have a single light bulb in this branch. This light bulb does not have to share that voltage with any other light bulb or resistor. So if we have 12 volts available here, how many volts is this light bulb going to use? If it doesn't have to share it, what? It's going to use 12 volts. It's going to use everything, all the available voltage. So what about this one? Same. Doesn't matter what the resistance value is because they're not shared with one another. These are independent. So if we added a third one over here and it had 12 ohms, it's still going to use all 12 volts available because it's not sharing that voltage with anything else in that branch. So the only time that you really have to worry about voltage drop is if you have multiple bulbs within the same branch, which is kind of not common. It happens sometimes. Okay, so this is going to be the number 12 volts. And there's really no math involved there. All you have to do is remember the rules and remember how the circuit works. If we really wanted to do the math, we could do so by taking our amperage and multiplying it by our resistance, and that would give us our voltage drop across that bulb. So if we took 4 times 3, it's going to give us 12. If we give 3 times 4, it's going to give us 12. So there's no need to do that. Anytime you've got a single bulb in a branch, it's going to have a voltage drop of 12 volts. So we can prove that over here on this circuit. If we power this circuit up, this bulb right here, it is not sharing anything with these over here. This one is a little bit brighter because it's an LED, has less resistance. But if we measure voltage drop across these 2 points, it's going to show battery voltage. If we measure voltage drop across these 2 points, it's going to show the same. If we measure voltage drop across this one, it's going to be slightly different, but only because it has a lower resistance, not because it's sharing the voltage. Since it's an LED, it's got some special character. These two would be the same. They're parallel to one another. They're exactly the same bulb, so they're both going to have an identical voltage drop. All right, so I will leave all this up here. And like I said, if you're a Shelby County high school student or if you're a Collins student, the ACT for Shelby County is tomorrow. So everybody except for 11th graders is going to be virtual. If you're a Spencer student, you're going to come as normal, or an eminent student, you're going to come as normal. But you're going to have a discussion, which is just going to be 4 questions that I want you to answer. That's going to be your assignment for tomorrow, and it's going to be based on everything that we talked about today. So you can write this stuff down, you can go back and watch this recording that I'm going to post, and you'll be able to find those answers to those questions. You're also going to be doing some experiments, just like we did on today's class with parallels or series circuits. There's going to be a handful of those as well that you're going to do, and probably answer 1 or 2 questions on those. And we're going to start building these probably later this week. So we're going to take everything on these boards that we have, cut them apart, and then we're going to rebuild them in parallel.